Student at Dalhousie University, and today I'm going to be talking to you about my ongoing research, where I'm trying to monitor the critically endangered Atlantic whitefish using environmental DNA. As this is a conservation showcase, I don't think anyone will be surprised to hear me say that biodiversity is in crisis, but I would like to preface this by saying that extinction in and of itself is a natural phenomenon, and we can see from the fossil record that the baseline extinction rate was about 1 species per million species per year, with the exception of 5 times in the Earth's history that had elevated species die off. These are the mass extinction events, and they're characterized by having more than 75% species loss in a relatively short amount of time, geologically speaking. Unfortunately, the current species extinction rates are even higher, and unlike those previous mass die-offs, current species loss can be attributed to human action, namely habitat destruction, pollution, overharvesting of commercially valuable species, the introduction of invasive species, and of course, climate change. Biodiversity is declining in all ecosystem types. However, I will just be focusing on freshwater for the context of this presentation. These are small but mighty ecosystems. Freshwater is a mere 3% of all the water on Earth, and yet it is home to 51% of all described fish. And unfortunately, nearly 1 in 3 of these freshwater fish are currently threatened with extinction. Nova Scotia is as much a freshwater haven as it is an ocean playground, with about 5% of our land covered by freshwater systems, and these are not immune to the biodiversity decline that we are seeing worldwide. Freshwater systems are also of particular concern due to the high human dependence we have on them. Not only do we get our drinking water from them, but they can directly and indirectly support people's livelihoods in the form of employment. So Atlantic whitefish are a member of the Salmonidae family, which means that they're related to salmon and trout species. They're one of only 4 freshwater fish endemic to Canada, which means globally they are found nowhere else. They're also the oldest lineage of whitefish, with estimates for their divergence from the common whitefish ancestor being put at about 15 million years ago. And therefore, they really represent an evolutionarily significant part of Canada's biodiversity. Not much is actually known about the habitat requirements for Atlantic whitefish. However, as they are historically anadromous, spending the summer months in the ocean before migrating up into fresh water in the fall for reproductive purposes, we can reasonably infer that they would require habitat accessible to each of these environmental types. Provincial fish surveys in the 20th century only documented Atlantic whitefish in 2 watersheds. But unfortunately, the Tusket River watershed population down near Yarmouth County no longer exists, leaving the Petite Riviere watershed as the last remaining wild population, and this population has become landlocked and they no longer migrate to the ocean. Zooming into the Petite Riviere, this is a watershed which has undergone extensive human development. To this day, it provides Bridgewater with their drinking water, and there is documentation of damming within the watershed going back to the 1700s. Atlantic whitefish have only been documented residing within the middle 3 interconnected lakes of this watershed, and together these 3 lakes span a mere 16 square kilometers in area. They are relatively shallow, with the deepest reaching 16 meters in some points, and when compared to other watersheds along the south shore, they are considered acidic. Although Atlantic whitefish reside within the 3 lakes, they do comprise one single genetic population. Atlantic whitefish in each of the 2 documented populations have encountered similar threats, but to varying degrees. The barrier to fish passage in the form of damming did lead the Petite Riviere population to become landlocked, as I mentioned, but the dams also meant that any individual who washed over the dam was lost to the population and therefore the reproductive pool, as they had no way to rejoin the population and get back over the dam. Habitat alteration is also a concern for this species, namely in the form of acidification, which can impact a fish's ability to take oxygen out of the water body, but also logging. Even though Atlantic whitefish are fish, they're still considered forest dependent because the loss of canopy cover due to logging can affect water temperature and oxygen levels, and logging can also cause sedimentation to get put into the water body, which can impact the water quality and the bottom habitat, which may have implications for spawning. And lastly, the introduction of aquatic invasive species is a concern for Atlantic whitefish, namely smallmouth bass and chain pickerel. I would now just like to take a moment to acknowledge the decades of work that have already gone into trying to help Atlantic whitefish recover. Although ultimately not all of these efforts were successful, they paved the way for what I am currently doing and have provided a lot of necessary knowledge. As you can see, I'm very late to the game with this species. I didn't begin my research until about 2020, and a lot of what I'm doing with environmental DNA is possible due to the knowledge that those before me gathered. And not only that, but the environmental DNA work we are doing is also benefiting from concurrent recovery plans and attempts for Atlantic whitefish that are happening right now. And so even though there's already been a lot of work that has been done and a lot of work that is currently going on, I wouldn't be speaking today if there wasn't a problem regarding Atlantic whitefish conservation. Namely, the biggest issue is that Atlantic whitefish are an elusive species and they're very difficult to detect. In fact, between 2014 and 2018, no adult was seen in the wild, although juveniles were collected, so we knew that adults were persisting and reproducing. There are also many biological knowledge gaps for this species in the wild, and that can make it hard to concentrate monitoring and recovery efforts for maximum impact. 16 square kilometers isn't a lot of space if that is your entire global range, but it's still a lot of water to cover when trying to search for a fish by dragging nets through the water. And so this is the issue that my work is trying to solve. But before I get into how environmental DNA is used, I first want to just go over what exactly it is. So environmental DNA, or eDNA as I'll be referring to it going forward, simply refers to the fact that as a fish is existing and living its day-to-day life, it is shedding DNA away from itself. Even after the individual has left the area, the DNA persists. And it persists not only in the water column, but it can also sink to the bottom of the habitat and accumulate in the sediment as well. And it's collectible from these two environmental types. As the fish is not required to be present at the time of sampling, this is a non-invasive approach. eDNA studies typically fall into one of two categories. The first is a single species approach, where the goal is to just find the DNA of a single species of interest. This could be one that is commercially important, or rare, or endangered, or invasive. The second approach is a community approach, known as metabarcoding. And the goal of metabarcoding is to identify all species which have contributed DNA to your environmental sample. But no matter which approach you're going to do, the single species or metabarcoding, you're going to follow a workflow similar to this, where the sample first has to be collected before the eDNA is isolated from it. We then need to amplify the DNA so there's enough to work with, and then analyze it. And so specifically getting into my research, the first step was to develop the eDNA tools in the lab. And I say tools plural because there's a trade-off between different DNA marker types, not only in regards to the specificity, which just refers to the fact we want to make sure we are only getting the DNA that we are targeting, but also the sensitivity, which refers to the amount of DNA we're able to detect within the environmental sample. So there are trade-offs in regards to those two things, but also in terms of the biological information we can infer from the eDNA output. And so my lab is working to develop 3 different DNA marker types, 2 which are focused only on Atlantic whitefish, and 1 which is a metabarcoding approach, so we can determine any species associations within the habitat. So after we developed our tools, we then needed to test them on water to make sure that they worked. And we were able to do this because Dalhousie is currently raising some Atlantic whitefish in captivity, and so we were able to sample that water. This was a great testing ground because we had Atlantic whitefish swimming in water, and therefore we knew that that water would have their DNA. But it's one thing for our eDNA tools to be able to work on squeaky clean aquatron water. But as the name implies, eDNA is influenced by the environment that it's in. And so by that, I mean that the rate of eDNA shedding and decay, as well as its detectability, is impacted by other environmental factors, including water temperature, pH, the amount of UV that the water is receiving, and the other microbes within the water. So we needed to test our tools on water representative of Atlantic whitefish habitat. And so luckily we were able to utilize ongoing Atlantic whitefish recovery work where juvenile Atlantic whitefish are being re-released into the Petite Riviere. And so before they were set free, they had to acclimate to the water. And for that, they were set in a net pen within the system. And so we went to that pen and we sampled the water directly in it. Not only did we sample within the pen, we also sampled in a transect moving away from the pen in order to see how far away from the source we were getting eDNA detection. And we were getting detection up to 80 meters away, which indicates to us that our tools are able to detect Atlantic whitefish in their natural habitat. So after testing our tools on some controlled samples, it was then time to go and actually sample some unknown locations in the Petite Riviere. We had two goals in mind. The first, which is we were trying to locate spawning grounds. The thought with this is that since Atlantic whitefish are broadcast spawners, which means that they directly release their reproductive material into the water column, there would be an influx of eDNA concentration when they were spawning. And so we sampled the locations denoted by the purple dots every week for 8 weeks, looking for a spike of eDNA concentration to indicate spawning activity was happening. We were also interested in determining how Atlantic whitefish detectability changed over the different seasons. And for this, we sampled the red dots there down in Menamkeek Lake every week for 8 weeks before and after the lake stratified. Atlantic whitefish are thought to prefer colder water, and therefore, when the lake stratified, the thought is that they would be concentrated beneath the thermocline in the cold water, and therefore would have increased detectability. And so after the samples were collected, it was then time to get into the lab and actually look at what we had within them. So currently I have collected the samples and isolated the eDNA from within them. But if we take our simple workflow here and zoom into a little bit, our different DNA markers have different requirements in the lab for analyzing the DNA within them. And so we've analyzed our samples with the targeted markers using quantitative PCR, which returns the concentration of Atlantic whitefish DNA within the sample. But we are also looking at metabarcoding so we can determine if there are any other species DNA present within our environmental sample. And so this brings us to where I'm at now. I have tested the tools on the aquatron water, the controlled water, and we have sampled the Petite Riviere, and now I'm working my way through analyzing the eDNA within those wild samples to hopefully be able to make some inferences about Atlantic whitefish in this habitat. Just finishing up, eDNA is a great tool with a lot of promise, but it's not the be-all end-all, and there are some pros and cons to it. It is really great that it's non-invasive and no animals are harmed during sampling. However, the fact we don't see the individual means that there's no physical information that we can gather. We do not know the age of the animal, whether it's a male or female, whether it's healthy or not. There are multiple applications, but also at this point in time, eDNA cannot really differentiate between multiple individuals of the same species within one sample. It is quicker and more cost-effective than traditional netting methods, but there are many unknowns for eDNA fate in the wild. But to summarize, freshwater ecosystems are very important, but they are losing biodiversity, and Atlantic whitefish are one such freshwater fish at risk of extinction, and eDNA is a promising tool to monitor them in their natural habitat. My questions? Any questions? Thank you for listening. My contact information is here in case you had any questions. Thank you for listening.